All right, I'm under condenser applications right now, and it really doesn't do you justice to give you a page of condenser applications in components, heat exchangers, and condensers. What I would urge you to do, and we're going to review somewhat, even though it's not there, you need to go to thermodynamics. Go to thermo and look up topics 3, which is steam. That's steam. And then you also need to look up topic 7. Go ahead, go to look up 7. And that's going to be heat transfer. Heat transfer. And those two, along with this topic, kind of provide a wonderful foundation for everything. But any of them by themselves really doesn't give you the whole picture. But what I'm going to do is I'm going to try and do my best right here to give you a one-page overview of condenser operation. All right? So what we have in our cycle of steam is we know, and I'm going to make it very small up here. Here is our reactor. And it is generating steam that is leaving down the steam lines. And yes, there's an inboard main steam line isolation valve. There's a containment wall. There's an outboard main steam line isolation valve. There are stop valves, control valves, bypass valves. But we're going to go to the high pressure turbine right here, high pressure turbine. Now, the operating pressure typically of a boiling water reactor in the United States is, nominally about 1,000 psia. And that's ballpark, a little higher typically, but this gives us a good operating temperature. The saturation temperature is 544 degrees, and let's assume the quality of the steam leaving the reactor is 100%, which means there's no water in it. It's 100% steam. The moisture content is 0. That is saying the same thing. Moisture content of 0, quality of 100 is the same thing. And let's say it's coming down the steam line at 10 million pounds mass per hour. So I'm going to put 10 e to the 6 pounds mass per hour. So it comes through the high pressure turbine, and I know that a portion of that energy in that steam is converted to rotational mechanical energy, or work rather. And then it exhausts out of the high pressure turbine. Now, if you'll look at your Mollier diagram, it looks something like this. The Mollier diagram in the back of your steam tables, right? And there's going to be a pressure line that goes like this, and it's going to be about 1,000 psia. Now, if the discharge of the high pressure turbine, the quality of this steam, as it lowered its pressure and the steam expanded across the turbine blades, and I converted much of the energy to rotational work, I started introducing moisture into the turbine. That's because right here at the outlet of the turbine is what's known as a moisture separator, and you may have a reheater. And if I said it's operating at 300 psia, what has happened is there's a 300-pound pressure line right here on your Mollier diagram, 300 psia. And you were operating initially on this big line right here, this thick black line on your Mollier diagram, and that is called the saturated vapor line. And it represents 100% quality, so you were initially operating right here. Now, right down here, the horizontal axis on this Mollier is entropy, and the vertical axis is specific enthalpy. So what happens is, and if it's an ideal turbine, which you don't have, none of us do, but there would be no change in entropy, but there's a change in enthalpy across it, it goes straight down. That would be an ideal turbine. There's no change in entropy, and it just extracted work out. And here's the change in enthalpy across the high pressure turbine. Then there's moisture now. These are moisture lines if you're looking at your Mollier diagram. And I have introduced moisture. So the moisture separator at a constant 300 pounds will go ahead and bring me back up and reduce the moisture of that steam. And if you have reheat, If you have reheat, it's going to continue to add energy, and it's going to take you into the superheated region way up here. Then, you know what's going to happen. We're going to come down here, and we're going to go to a low-pressure turbine, followed by your condenser. That's what's going to happen. Well, if you just have a moisture separator, here's your condenser pressure way down here. Let's say it's 2 psia. So now you're going to do the low-pressure turbine drop is going to go like this. And this is if you just have a moisture separator. However, the inlet enthalpy would be way up here if you have a moisture separator reheat. And you can see this would be the change in enthalpy. So you really do get a lot more work, because work is proportional to the change in enthalpy out of the low-pressure turbine than you do the high-pressure turbine. The purpose of the condenser is to maintain a vacuum, a really low vacuum, because if I was at atmospheric pressure, there's the atmospheric pressure line. The change in enthalpy across it would be right there, and you wouldn't extract near as much energy out of the steam as you do when you put the condenser at a vacuum. Now, this is discussed in excruciating detail in topics 3 and 7 of thermodynamics. But this is just kind of a layout here. The reason we operate this condenser at a vacuum is to extract more work out of this low-pressure turbine. We have this 300 pounds here and 1,000 pounds here, so we have a 700-pound pressure drop across the high-pressure turbine. And that allows us to extract this much work, because you can see the 1,000-pound pressure line and the 300-pound pressure line. But operating this at atmospheric pressure wouldn't allow us near as much work to be extracted. So increasing the work of the turbine is one reason we operate our condenser under a vacuum. If you're looking right here, produce a vacuum at the turbine exhaust for improvement of overall plant efficiency. Well, plant efficiency is equal to the net work that I get out versus the heat that I add. So if I can get more work out of my turbines, I can get a better plant efficiency. And operating under a vacuum allows me to get a lot more work out of my low pressure turbine when my condenser is operating at a vacuum. A couple other things it does. It says, condense the turbine exhaust steam for reuse in the closed cycle. Yeah, I need to pump that water from the condenser, so I know that as the steam enters the condenser, it's going to condense, and there's all these tubes right here, and at some point the steam has condensed. There's all this steam in here, and now it's water right about here, let's say. So I got blue water, and then it actually subcools, and I actually end up with some subcooling, and that allows me to prevent cavitation of my condensate pumps. Also, the condenser, once it enters here, it's going to allow deaeration, to deaerate the condensate. And I know that steam jet air ejectors can take a suction on this, and I can remove the air and non-condensable gases. Another thing is it allows a certain amount of stay time for nitrogen-16 decay gammas. So I'm not transporting these gamma emitters around the plant. I'll allow them time to decay away. So condenser application has a lot. Now, if you look at the K&A's principles of the operation of a condenser, excuse me, we really need to know what's going on. In real life, it's very basic. I have a condenser water box, and I have giant circ water pipe, and it might be as large as, say, 96-inch pipe. We're talking 8-foot pipe that comes into a giant inlet water box, and there's a tube sheet right here. And there's thousands and thousands and thousands of these tubes that circ water flows through in the condenser. That's the inlet tube sheet. And then at the outlet, I've got an outlet water box and an outlet tube sheet. And then there's water from the circ water, it leaves. Let me make it look pretty. Let's make this look better. There. And I know my low pressure turbine is sitting right here, and steam is coming in, going in the center, goes out, and then it exhausts into the turbine. So I've got steam dumping right into here, so it's steam bubbles right here after work has been extracted out of this turbine, and I've got motion. And at some point, all of the latent heat of vaporization has been removed, and I've got water droplets, and before you know it, I'm starting to increase the amount of water that I have, and then I go to the bottom of the condenser here, and I've got water. And then the condensate pump, wrong color, the condensate pump can take a suction right there, condensate pump. So the condenser is a really useful tool in our steam cycle, a component rather. It serves a lot. Keeping it under a vacuum is going to allow us to extract more work out of this turbine. It's going to allow de-aeration of that condensate as air and non-condensable gases come out of solution. We can take a steam jet air ejector and we can get rid of those air and non-condensable gases. So lots of useful purposes. The relationship, if I had to talk to you about condenser vacuum and back pressure, the higher the pressure in the condenser, the less work you're going to get out of the steam. So after the steam condenses, obviously the saturated liquid is going to continue transferring heat, and we're going to subcool somewhat. That's called condensate depression or subcooling of our condensate. And about 10 degrees of subcooling is desirable. Any more than that, and you're just throwing away heat that the reactor is going to have to make up, and that's going to cause plant efficiency to go down. Any less than that, and you're really getting close to cavitation potentially in your condensate pump. And like I said, check out topics 3 and 7 in thermo to really get a handle on this. Okay, this should really be a discussion about the components and how the condenser is made up of an inlet water box, an outlet water box, 2 tube sheets, and with the tubes going across the condenser. And I'll tell you, we generally put feed water heaters, low pressure feed water heaters in the neck of the condenser because it just makes sense from an economic standpoint. But we'll talk about that later. All right, next topic, next video.